Is it visible? The slides?
Yes, sir, visible.
Yeah. So today I have switched off my video. So I think that's okay. So I'm just giving only the slide. So keep our bandwidth also low. Yeah. So let me. Now we are going to. Just before this, if you go into the syllabus, we are almost halfway or more than half of the first unit of the proposed paper. Uh, so another one or two, three, four lectures will be winding up our discussion on the first part. That is, the unit one will be over. So again, we were going a bit slow. Normally, we don't take this much time to finish that unit, but from my side, I'm going a bit slow so that you get a feel of you understand things better. So that is the idea. Now, today we will be discussing two aspects. This was pointed out by Bhaskar uh, in the last lecture. That is about failure of Ohm's law, or what happens at high fields. So that is uh, one aspects we will be discussing, and then we will go into there are other ways of conductivity, modulation, etc. So these two aspects, and we will discuss today. So important thing we have discussed in the last lecture was, see, you have the thermal velocity of at room temperature and above. Carriers have thermal velocities, and thermal velocities are quite large. We have seen the values of that. And then when you apply an electric field, it uh, gives a directionality and the drift velocity. And if you work out that problem which I have given you, you'll see that the drift velocity is very small, even for the moderate electric fields. It is quite small as compared to the thermal velocity. So it is a small perturbation to the thermal velocity. So that's a important thing we have seen. So then only we talk of a drift motion of the carriers. That means the most important thing is we have seen the expression for the microscopic mobility. There we have introduced a parameter. There are two parameters coming into picture. One is the effective mass, and the other one is the time constant, which decides the time interval between the scattering, because we have seen that carriers are moving in a medium where they get scattered at periodically with a certain time constant, etc. So we have attributed a mean free time and a mean free path, etc. And if in the absence of the electric field, there is no net display under the carriers, we have seen. So the fundamental assumption under low field transition, that twice or the time constant is independent of the electric field. The scattering events are not changed by the electric field, or the electric field has no influence on the scattering events. So it is a small perturbation to the thermal velocity. That was the. Now, at high electric, see, the low electric field, what happens is the carriers get energy, they pick up the energy from the electric field, they collide with the or interact with the colliding. Don't When you talk of collision, it doesn't mean that actually physical collision. They are coming into interaction because it is basically electrostatic interaction. So that is why we use, instead of collision, we are using the term scattering. It's not that they are going and colliding, but then like the picture we have used is the momentum transfer or the momentum conservation, etc. There it appears like a kind of mechanical collision, but term in physics which we use in this case is scattering. So the scattering rate, but at low fields, this scattering take place and the carriers are moving. But when we increase the electric field, the energy gained by the carriers could be high, and then uh, situation will change, and it is seen that it is changed. That is what we are going to discuss in the first part of our presentation today. And one of the important consequences or variation which we'll see is the failure of Ohm's law or deviation from Ohm's law. That see, the Ohm's law assumes that a carrier move with a constant mobility, and if you see the velocity versus electric field, the slope of that will give you the mobility, because mobility is nothing but the velocity per unit field. So slope of the curve, velocity versus the electric field, will give me the mobility. So we can see that if Ohm's law is valid, mobility of the carriers will be constant for the given temperature, etc., for the given material. So it is independent of the electric field. Failure of Ohm's law means the mobility changes with the electric field. So it is changing. So that is so. What are the ways? What is happening, and what is its consequences? That is what we'll see. So, important thing we need to understand is uh, the carriers are gaining energy, and they are not able to transfer it instantaneously to the surroundings. That is through collisions. They are not able to transfer that energy gained from the electric field to the surroundings. So we talk of thermalization or hot carriers, which we have mentioned last session also. The carriers are not in equilibrium with the surroundings. That means their temperature or energy. We very often talk of a temperature, but the meaning is they are at a higher temperature, a higher energy than the surroundings. Because actually, at low field, your surroundings act as a heat sink. So immediately, whatever energy is gained instantaneously, it is supposed to have been transferred to the surroundings. But if the electric field is high, then that doesn't happen instantaneously. So there will be the carriers will be having energy higher than the, or they will be not be in equilibrium. So now the thing is, they then you talk of we have seen that various phonon phenomena, like phonon means lattice vibration take place. So at low fields we have the acoustic phonons only, which take away the energy from the carriers. So when energy gained by the electrons are high, especially when under high electric field, then it it can transfer its energy only through optical phonons. So excitation of optical phonons take place. The energy transfer through optical phonons takes place. So there will be large loss of the energy. So you will see that then the velocity gets saturated. That means you will have the carriers are moving with a constant velocity. So this has been seen in many of the materials. It was always there that this kind of nonlinear phenomena, deviation from Ohm's law, etc. So the carriers are moving at a constant velocity. So very often we call it as scattering limited velocity. So you might have seen, like you might have studied in your schools or in colleges in physics about the parachute movement, moving like paratroopers, how they come down. Do you have any idea what happens there? Hello,
Yes, sir.
paratroopers. The parachute is coming. Yeah, it comes with a constant velocity, isn't it?
Yes, sir. Yes, sir.
Yeah, how it happens?
But due to air resistance.
Yeah. So actually, you have they attain a terminal velocity because what happens is there is a gravitational pull, or the acceleration due to gravity is there, and then air resistance which act. opposite to the motion, so that at a particular point they got both will get balanced, and so it is a kind of dynamic equilibrium. Acceleration due to gravity and upward thrust due to air, they balance, so it comes with a constant velocity. So it is not exactly similar in this case, but you see that their carriers are moving with a constant velocity, and then it depends on the material, because effective mass of the carriers in different materials are different, so the saturation velocity for different materials are different. So this is one important thing which happens. So you have a, now the question is, see, we will be looking into other high field effects also, but one important question comes is why we are concerned about it, because normally we are dealing with volts to millivolts only. So why we should be worried about this high field effects? So because when you talk of a semiconductor device or a semiconductor integrated circuits, you are dealing with few volts or millivolts for that matter. Across the devices, you may have few millivolts only, or maximum few volts. To current technology, it is around zero point 0.2 volt only. The supply voltage itself, that is the highest voltage, that is around zero point 0.2 volt only. So then, why we are worried? Any answer to that?
So when we reduce the size, then the
Yeah.
channel width is too small.
Yeah.
Then a
See,
small amount of
actually,
voltage will build that.
yeah. So they actually we are not talking in terms of the voltage. We are talking in terms of the electric field. Electric field depends on the applied voltage as well as the dimensions. So that is volts per length. In simple terms, you can say that. So when the length is reduced, naturally the electric field given a particular applied voltage will increase, and we are not dealing with centimeters or meters, we are dealing with microns or nanometers. So that means naturally the electric field experience will be, one can always do a rough calculation. If for example 1 volt applied across 1 centimeter, then you can find it out across 1 millimeter, then 1 micron, and then 1 nanometer. You can see that the electric field will be changed drastically into many orders, because millimeter and centimeter of the order of 10 raised to 2, then micron 10 raised to 6. So that 6 orders of difference in the electric field can take place. So you experience high electric fields. You can experience it, it depends on the dimension. So we have to see that that the dimensions play a very important role, even though the voltage you are reducing. See, each generation you are reducing the voltage, but then electric field is still increasing because the dimensions are also reduced, and they are not in proportion actually very often. So again, we a little bit, because this is we need to keep this high field effects in picture always whenever you are studying about different integrated circuits. So I'll be spending some time on this. We will be revisiting it when we study about the MOSFET and other devices or microelectronic devices. So the basic foundation for that we are doing today. So that is why I am spending some time on this. So when we talk of microelectronics, two contradictory things are happening. What are the contradictory things happening? One is you are reducing the uh, dimensions, and one more thing is happening. The voltage, of course, to keep the electric field as far as constant, you are reducing the voltage. What is the other thing which is happening in the subsequent generation of, for example, if you take a microprocessor as an example, the benchmark device, suppose for the most of the time, microprocessor is taken as the benchmark device to show the progress of microelectronics. What are the two contradictory things happening in microprocessors, or what are the two challenging things? It's contradictory, may not be the right word, but what are the two things happening in microprocessors? Have you noticed in the different generations? Say, for example, you have started with 8 6 generations of processors. So What was happening in each generation? Because you have in your BSc you have studied about which microprocessor you have studied in your BSc?
8085.
8085. Then you have seen 86. It's like that a series of coming to Pentium, then multi-core and all those things. What are the two fundamental things happening? CA 85,
The
86, and
processing power is
yeah.
increasing,
How? Yeah,
but
processing power.
power
Definitely. Yeah,
consumption is decreasing.
yeah, that is true. Now the question comes: how the processing power is increased? One technique which is used, which you can see easily.
Uh,
Extra. Yeah.
clock frequency is increased.
Exactly. That is what the answer I wanted. There are other things are also happening, but then we are going in a very fundamental way. You were in each generation, you will see that the clock frequency was increasing. So, what will happen when you are increasing the clock frequency? The speed definitely will increase. So now, in our context, is has it got any implication? So we are discussing about the high field effects. So, has it got any consequences in our context? The increase in the frequency, because two contradictory things which I wanted to discuss was one is the dimensions is uh, and second is the clock. Dimensions you are reducing, at the same time you are increasing the frequency. So when you are increasing the frequency, so what happens to the
The
device?
capacitance plays an important role.
Pardon?
Capacitance
Yes,
of the
capacitor.
transmission plays an important role.
Yeah, that is external to the device. See, actually, again, I mean, that is there, but effect of capacitance and all those things will come into picture. But we are going in a very fundamental thing, that is, your electric field is changing very fast, because the clock means the switching. See, basically, clock is like, as I told you, it's like a teacher who will decide that how fast other things are happening. So that means your signals are also changing very fast. Signal changing very fast means your electric field is also varying with that frequency. Do you agree with me? Your switching speed, that means the electric,
Yes, sir.
the signal is varying that fast. So that means your electric, in simple terms, the electric field is varying very fast. It's of the order of that frequency. So that means simultaneously you are increasing the electric field as well as the frequency. So that means the electric field is also quite high, and frequency is also quite high. So this will come together. And actually, I mean, we have seen that, and typically it was we will be seeing, or you are aware that around roughly around 18 months or so, the next generation was coming, thanks to your Moore's law and things like that. So your device or your system was becoming obsolete. What is the meaning of obsolete? What is the meaning of obsolete? Have you heard of this word obsolete?
Sir, coming to an end.
Coming to an end. Yeah, right. In the end means it cannot work, or what is the mean? Is it like that, that it cannot work? You are
It will be slower than the current generation.
yeah. See, obsolete, I have put in the slide, you will see that obsolete means like me. So what does it mean? Any
But sir,
guess?
still you are faster than us.
Which is no longer in use.
Yeah, no longer in use. Why it is no longer in use? Is it because it is not functioning, or what is the use? What is the problem?
It
Outdated.
cannot hold
Yeah,
applications
actually,
that
obsolete means old.
outdated.
Getting old. That is why I use the word like me. See, because you feel okay, this person has become old, and because there are others who can do better performance. So that is the meaning. It's not that it is not working. See, this has been a very tricky problem in this microelectronics, because your devices or the circuits have, especially the chips, have infinite lifetime. I mean, very large lifetime, provided you work it in the voltage and current ratings are followed. Most of the time, they are they can exceed the durability is quite high. Actually, I might have shared with you my experience with one TV. I wanted to change it. Actually, my wife was not accepting it because he said it is working fine. Why you want to change it? So that is a problem. It won't get like it won't get spoiled or something. Performance is there, but you are coming out with something better. See, like in terms of the speed, as he has mentioned, in terms of power consumption and things like that. So that is the meaning of obsolete. It's not obsolete doesn't mean that it is very important, that it is not functioning. It is functioning, but the way it used to be. But you have a better thing, which gives you have a performance. Because normally we talk about performance in terms of power consumption. We talk about performance in terms of speed as far as the microprocessor is concerned. So that was you have seen that because this portability has increased and the things like that. I don't have to tell you the advantage of those things. So this we should keep it in mind. So, but anyway, that was a separate thing. So your high voltage, high frequency effects comes into play. See, we have to understand in the in the last discussion, we mentioned that the carriers are picking up energy from the electric field and they are transferring to the surrounding. And we have assumed that it happens instantaneously. And we know that nothing happens instantaneously. There is a time associated with that. You got the point? That there is a time. It takes some time to happen. First, it will pick up the energy. You talk of energy relaxations and things like that. There are two things happening here: momentum as well as energy. So they have relaxation time associated with momentum as well as the energy. So now, if your field is changing or time of change of electric field is much more than the your the characteristics I'm involved in the transport process, things are going to be in trouble. So this high frequency means that is what is going to happen. That by the time the carriers are relaxing, before that the electric field is changing. So this is it has also some consequence. We have already seen the hot carrier effect. Now this high frequency, high field can create other complications. So you got the point?
Yes, sir.
So this is very important for you to understand, because we were not only increasing the electric field, we were increasing the frequency also. So both this will have consequences. Yeah, that's what. So this, as far as the field is concerned, this is what is happening. As you increase the electric field, the velocity becomes constant. That is a scattering limited velocity for electrons as well as holes. There are separate values, and this is for one particular material. For different materials, you'll see that the velocity saturation will be different. The saturation velocity is different. There will be a threshold electric field above which this velocity saturation happens. So, do you feel that that affects our device performance in any way? This again, we need to see. I am assuming that many of the things you are aware. I'm just bringing it to your notice only, because it's not like when you are in the first semester, first time studying all these things. So that is why I am taking the example of microprocessors, many other things we are bringing in with the assumption that you are aware of it. So what is the consequence of velocity saturation as far as the performance of the device is concerned? Any idea or anything you want to say? Already we have mentioned the performance is decided by two factors. We have put some conditions. See, one is the speed and the other one is the power consumption or area consumption and things like that. So these are the some of the performance criteria. So will the velocity saturation affects it anyway? The performance, will it make any difference to the performance? Yes. Hello. You got the question?
Yes, sir.
Yeah. So will the velocity saturation matters in performance? Will it make any difference to the performance of the device or the circuit. Yeah, any idea?
So the maximum current in the saturation will be less if the
It will be
resistance.
limited because we have seen that is one thing. The current will be limited because current was decided by the carrier concentration and the velocity, isn't it? The velocity. So that means if you want more current, the carrier concentration has to increase because if you go look at the current density equation, current density is decided by carrier concentration multiplied by the velocity. So if you want to increase the current density, okay, that is one thing. Any other thing? The current will be limited. Yeah. Any other thing? Yes.
For heat,
No, no. Heat is different thing. I'm performance because the velocity is heat anyway. Because the velocity is limited, it is not going. Velocity is not increasing. It is constant. So how it can increase the heat?
So power consumption.
How power? I mean, we justify it. We have to justify it. How the power consumption will increase? So you have to go back to your school. See, for example, I want to go to from Ambala to Delhi or Kurukshetra to Delhi. So I go by a tractor. How much time I will take?
yes, sir. I understood, sir. So the channel it have to pass the more the speed, the less
It
the
has
time
to
it
be
will take.
fast. See, actually, fundamental level, how fast the carrier move from. We take the example of MOSFET. How fast the carrier move from source to drain will be deciding the switching speed. Because the basic level, what is happening is your certain number of carriers are there in the source. They will have to reach at the drain. In the MOSFET example, similar thing can be talked of BJT also, but today we are talking of MOSFET because most of your microchips are made of MOSFET, especially your microprocessors are made of MOSFET. So the the basic time is decided by how fast you can move the carriers from source to drain, and that is decided by the distance between the source and drain and the velocity, how fast they can move. We talk in the layman terms, we talk of speed. See, for example, we have to go to Kurukshetra to Delhi. If you want to reach faster, we will increase the speed, isn't it? Because you cannot change the distance between Kurukshetra to Delhi. Okay. Whereas there you increase the speed, but if the speed is limited, then we cannot get by application of a higher electric field, you cannot get higher velocity, so transit time get I mean constant. So there we have to reduce. That is why we were reducing the channel length. Actually, we were bringing source and drain closer so that your speed is. But that was one thing which was happening in the each generation of microprocessors, that your source and drain were coming closer and closer. It was creating another additional problem that we will be seeing later. But this was one of the reasons. Your velocity saturation effect, the current saturation takes place, then the speed is limited by the velocity. So one of the fundamental consequences of velocity saturation is your uh,
Switching
speed.
time.
So switching time, you can say in digital, especially the digital systems, you talk of switching time. Switching time is not changing because of this problem. So then you have to go for different materials, like which is having higher saturation velocity. Which material will be having, as you have come across 2 3 materials, which materials will have higher saturation velocities? Any guess? Yes. See, we have seen 3 semiconductors: germanium, silicon, and gallium arsenide. So which you expect will have a higher uh,
So
saturation
gallium
velocity?
arsenide.
Gallium arsenide is definitely, because that again, If you remember the table, the effective mass, then the thermal velocity, all those things are higher in gallium arsenide. Germanium also has, but then germanium is not a very like popular material. Gallium arsenide has better performance. So gallium arsenide can be, but then microelectronic circuits with the gallium arsenide is not that popular. That is, of course, another story. But from the material point of view, this gallium arsenide can give you a higher switching speed. So, in fact, it is used in microwave devices. We'll be discussing a little bit about it today, but you will be studying in more detail in the other paper on microwave devices. Anyway, so this velocity saturation is a very important issue as far as microelectronics is concerned. So it has consequences in two ways. One is, as Prashant has said, the current density is going to be limited. If you want to increase the current density, then you have to increase the carrier concentration. That, because increasing the carrier concentration again has different consequences. So you don't like to do that. So it is going to limit the current density. Yeah, and second thing is, of course, the switching speed. Yeah. Now, other thing is the transient. This it is about time. So this is as far as the frequency behavior is concerned. Uh, you can see that with the electric field. So you see that this is uh, this is about the velocity overshoot. Have you seen in any of these circuits this kind of velocity? Not the velocity, some overshoot phenomena. Those who are familiar with some circuits, they see this. Which circuits show this kind of behavior? Yes, this overshoot, and very often we talk of overshoot and undershoot. Where you see this, which circuit shows this?
Sir, MOSFET.
No, MOSFET, why, like the basic element, basic circuit, MOSFET also may show, but normally in the lab, I don't know whether you have noticed this. If you see some of these RC circuit capacitance, when initially the capacitance is like a short, so then these kind of phenomena are seen. When undershoot and overshoot is shown by RC circuit. If you see the transient response, if you have a good oscilloscope and if you see that, or if you use a storage oscilloscope for the RC response, then you see this overshoot and undershoot of the current. There it is about the current, or the here it is about the velocity we are talking. That is already different. So this is because what we have said earlier, that it's the carriers are not able to see. It is going to steady state value. That is a constant. It is going to steady after a few seconds. It will go back to. Sorry, it's not second. It is in picoseconds, mind you. The time of the order of picoseconds, not seconds or microsecond. It is picosecond. In fact, this results. Of course, it is not from my thesis, but the same kind of study I have done my PhD. During the PhD course, I have also obtained same kind of, through simulation using the models, I got same kind of results. When I was preparing this lecture, it reminded me of my work also. Same kind of thing I have obtained. So the thing is, these see that uh, it takes some time for the carriers to reach the steady state velocity. This is steady state. It is not the saturation limited velocity we are talking of, because the graph is between velocity and the time here. So don't misunderstand this, that it is about the steady state velocity, that is, which we talked of, that carriers are getting instantaneously, they will pick up the velocity. So it takes some time to get that. So before that, they go through that velocity overshoot effects are there, and it depends on the electric field. You can see that higher the electric field, higher will be the velocity overshoot. Then you see that during that interval, the velocity of the carriers are much higher than the steady state value. It's not saturation limited, it is much higher. So if you multiply with time that velocity, in that distance, the carriers are moving with faster velocity. So that means it can show, it can perform better in that space. Here it is around zero point 0.5 picosecond. 0.5 picosecond into velocity. That you can find out. It will come into some nanometers. So in that region, the carriers are moving with a higher velocity than the steady state velocity. So the switching speed in that, if the device dimensions are of that order, or there the switching speed can be higher. So we very often we talk of ballistic transport and things like that. So the last class we have discussed something about the ballistic transport. So this is consequences of high field, high frequency effect actually. So this is velocity overshoot is seen. Yeah. This is an important thing. So other one was the velocity saturation. This is second thing is the velocity overshoot. So you can see that again if you see the first two diagrams. So velocity saturation. So first thing is velocity saturation. Second thing is the velocity overshoot, and an extension to that is the ballistic transport. So these three things happening. One is the velocity saturation. Second is the velocity overshoot, and third is the velocity ballistic transport. So here, of course, when the dimensions are very less, there is no scattering will be, or a very limited scattering will be there, so the carriers can go with a higher velocity. So that is the idea. So very often we talk of hot carriers. All these things are related to especially velocity overshoot and your the third one, ballistic. Both are related to, both cases can give in a hot carrier effect. Again, this is a very important phenomena in most devices today. So there are like it actually something around 2006 or 7. I don't remember exactly. They came to realize the importance of this hot carrier effect, and suitable uh, structural modifications and other things were introduced to reduce the hot carrier. The idea is, see, especially for MOS, hot carrier you understand, last lecture also we have discussed about the hot carriers. But hot carrier, the consequences of hot carrier is the carriers are having energy much more than the normal thermal equilibrium energy. So when suppose they are moving from source to drain, they can behave very badly in the sense they can get into the oxide layer. They can cause impact ionization. That means they can break the covalent bond and create additional electron hole pairs. So all sort of things, and that in turn can cause additional leakage current, etc. So one of the main consequences we have seen is they get into the oxide layer, or between the source and drain. When they go, they get into the gate oxide, and then if the charges are present in the oxide, the threshold voltage will change, and you will see that gradually that device start failing, because as you use it frequently, more and more carriers get embedded into the oxide layer. The oxide quality deteriorates, and this kind of long-term reliability of the device was in question. So all these things, basically what is happening, they have sufficient kinetic energy, they get to jump over the barrier from channel to oxide, or they can cause impact ionization. So these are the main consequences of the high field effects in especially in silicon. Here I will mention one more high field effect of high field, which is not seen in silicon but in gallium arsenide. Why I am bringing in gallium arsenide is because you will be studying it, so I thought I should give you an introductory idea about it. You will be studying the microwave devices. Have you heard something called gun diode? Gun diode. Anybody heard of gun diode? Yes.
No, sir. No, sir.
Sunay? Eh?
No, sir.
Yeah. So anyway, you will be studying. So I will not go into the much details, but I'll give you. It's a high field effect. So gun. It is after the. It is not GUN gun. It is the name of a person. So double N is there. So you have a kind of it's typically shown by N-type gallium arsenide. So actually, I'm sorry that figure left side slightly got cut. So it is the again electric field or voltage versus the velocity kind of graph. So initially it was behaving like a normal semiconductor. Your velocity was increasing. Here it is again a kind of thing. So then you see that after certain value of the electric field, the velocity is decreasing here. So this is known as the uh, gun effect. So you should show a kind of negative resistance region. So this is used for, you know, that your basic understanding of electronics tells you that such devices can be used for making oscillators, negative resistance. So whereas this happens in a very high frequency, so it is used for microwaves. So gun diodes are popularly used for making uh, microwave devices. So you will be seeing in the microwave paper that the more detail you will be studying. Here, important thing is we have seen the last week, we have seen the energy band structures. We have seen that there are multiple uh, bands within the conduction band. So when at high electric field, the carriers can move from, very often we talk of a valley, from one valley to higher valley it can go. Then, and again we have seen that the curvature of the energy band diagram decides the effective mass. So generally the mass will be when you go from one valley to another valley, the mass will be decreasing. Whereas in this case, you will see that the effective mass of the carriers will increase. Increasing means the mobility will decrease. So the velocity will be decreasing. So that is how this is happening. So this is again a consequence of high field. So these are the some of the high field effects which you see in semiconductors: velocity overshoot, velocity saturation, ballistic transport, and then this is only in gallium arsenide, the gun effect. And gallium arsenide, I think indium phosphide also shows this kind of behavior because of that. This is a directly from the energy band structure one can infer this thing. So these are the kind of high field effects which we see in semiconductor. Any questions?
No, sir.
Now, see, so far, actually, we were talking about semiconductors and whatever things we have said. It doesn't make much sense as far as the our electronic systems are concerned, because we don't know how these semiconductors are special from the point of view of electronic applications. Because nothing none of these. For example, one of the most important property which we have seen is the temperature variation of the conductivity, isn't it? We have seen that, okay, when you increase the temperature, that is the only special property we have seen so far, that when you increase the temperature, or the conductivity of the semiconductor material increases drastically. In fact, we have seen that an exponential kind of increase. We have quantified it also. We can things that it depends on the band gap and things like that. But that doesn't make much sense from application point of view. Even if, okay, conductivity modulation could be good, but then we are not going to use temperature as a parameter for doing our processing actually. So that doesn't make, even though we a whole lot of time was spent on discussing that, but that is not the main thing. We can immediately conclude that that is not going to help us in making useful electronic circuits or systems. So we need to understand what makes it. Now we are coming to one of the most important aspects of semiconductors that that makes it special. So again, we are looking at the conductivity modulation because we are interested in the current the change in the electrical characteristics. So we have been using uh, conductivity as an important parameter for that. And one way of modulation was temperature. But very interestingly, Another very interesting thing is possible in semiconductors, and that is in fact the most important utility of semiconductor is you can selectively add foreign atoms, and you can change the its electrical behavior, especially the conductivity can be modulated, and the conductivity modulations gives rise to different kinds of properties. That is thing. So that aspects we will try to see. So again, we will try to see it in a very first we will see it in a very fundamental way, the qualitative part, and then we will quantify those things. I mean, which could be useful for making devices and. So, have you heard of solutions? What is a solution? We study about it in high school chemistry. What is a solution?
Mixture.
Yeah, solution is a mixture. So what is the kind of mixtures we can make? So when you talk of a solution, what comes to your
Liquid
mind?
solid.
Yeah, it
Um,
is. Yeah, it is a liquid and a solid. Then
then liquid.
liquid is possible. Solid is possible.
So like alloys.
Yeah, it's a, alloy is the best example. So solid solutions are possible. Alloy is the best example of. So you tell me what happens in a solution, because if you put say for example sugar or salt to water, you don't see the sugar, you don't see the salt, but you know that it is there. So what happens to sugar and salt when you put it
Sir,
into? Yeah,
sir, the gap between the molecules they adjust.
yeah, they go back. So you know that there are a lot of empty space available, and they go to those empty space, and uh, like can it go on indefinitely, or there is some restrictions on the amount of mixing you can do?
No, sir, not. Sir, when the it is tightly packed, then it will not.
Yeah, that's really because it is going to the empty space. Then there is a limit. After that, it will precipitate, and then if you want to further increase their capacity, how will you do? You want to add more, then what will you do?
So then we have to
Temperature.
increase the temperature when it becomes saturated.
Yeah. So once see, very often we talk of saturation, because why I am saying all these things, you may wonder why I am discussing, because this has implications in the things which we are going to talk about. So in a solution, what happens is, that it goes to the empty spaces available in between. So you talk of very often talk of a solid solubility limit. That means a solubility limit, not solid solubility. This is a solubility limit. In the traditional sense, we talk of a solvent and a solute. Solute is, for example, our case, it is salt or sugar is the solute. Solvent is water. So uh, there is a solubility limit of solubility limit is there. That means it gets saturated. We talk of a saturated solution. That means if you add further, they will precipitate. And if you want to increase the solubility limit, you have to increase the temperature so that more space is created so they can go. And when you decrease the temperature, or when it cools down, it will come out, precipitate. So this is the typical example we can use for in our case also. So here we talk of solid solutions. That means both are solids. We are introducing like us probably Nidhi was telling about the alloys. So alloy is a classic example of solid solutions here. So now when we talk of solid solution, there are three kinds of things possible. It can be alloys, it can be a compound. It's not a solution basically, but it's combination of two metals are possible. That is way I'm seeing it. So what is the difference between an alloy and a compound? What is the difference between alloy and a compound?
Sir, in compound the reaction is.
Yeah, there is a chemistry involved. There is an exchange of electrons. There is a chemistry, and important thing is in the case of compounds, their chemical properties are different from the host. Say, for example, if you mix two elements and the compound formed, they will be translated like hydrogen and oxygen. I mean, of course, it's not an example of a solution. I mean, I'm just taking this example. Hydrogen and oxygen, and when they form water, they are totally different. Same thing is true for two metals also. When their chemical compound is formed, their chemical and physical properties are totally different. And what alloys, the chemical properties remain the same, whereas the physical properties you will be seeing some difference. And some example. What is the difference between this brass and bronze? What is brass? Is it a element or is a uh,
Sir, it's an
compound?
alloy.
What
Alloy.
is how you make brass?
Sir, copper and
Copper and is a copper alloy. Copper mixed with
zinc. I
that
don't know,
is
sir.
copper and zinc will give you brass, and bronze,
It's
Copper and tin.
tin.
copper and tin. Actually, you see both cases there is copper. One when copper is mixed with zinc, it gives a certain different kind of physical properties. These are all physical properties only. It's a solid solution. Again, you have certain ratio of combination of brass and copper and zinc. Similarly, in the case of bronze, again, tin is one of the main. Apart from copper, tin is one of the most important constituent used. And steel, what is the steel made of? Stainless steel. I'm talking of. Yeah. Is it
Iron
a
and
pure? If it's a pure metal or it has some mixing or it's an alloy?
आयरन एंड कार्बन का सर एलॉय होता है ये.
Yeah. This is again steel is an example of iron and carbon. You can see that iron and steel, there are a lot of differences in their physical properties. See that again when we will be discussing, well, later on we'll be seeing that silicon germanium alloys can be also formed. There are specific properties associated with that. So we have seen alloys. Basically, they are solid solutions, and then you have compounds. They are totally different from the alloys. Now comes doping. So how doping is different from alloys? Yeah. Is the what is the difference between alloys? Say, can I say? Suppose you are all aware of introducing phosphorus or boron into silicon. Can I say an alloy of um, silicon and uh, phosphorus is formed when I introduce phosphorus? What is the essential difference between alloy and a doped semiconductor?
Sir, in doping, we are changing the properties of the material, like conductivity is controlled.
Yeah,
But in
clear.
but when we are making the alloys, we are somehow making the element better in terms of
The
ductility.
physical property. So there only the physical properties are changing. See here,
Yes, sir,
important thing
hardness.
is doping means by adding. See, the important difference is coming from the percentage of external element you are adding. In the case of if you see that brass, bronze, or steel example, of course, major host material will be copper. A good percentage. We can. I mean, I don't remember the ratio, but one can always find out the ratio of copper and zinc in brass. Similarly, tin and copper in bronze. One can and steel or etc. So one can see that. But you will see that the percentage is quite high. The percentage of the elements you are adding is quite high in the case of alloys. Silicon, similarly, in the case of silicon germanium alloys also. Whereas in the doping, the percentage of the foreign atoms or the impurities you are adding is quite small. That is a very important concept. And then there are other differences also. So they will be we are getting into that. So the percentage is like even though it is not a very good example to quote, uh, you see that see people who take drugs. I mean, I'm talking about psychedelic drugs, a small amount, milligram or micrograms or milligrams especially, make the drastic changes in the personality because it affects the brain or the neural system. So they behave very different fashion. For example, those people during the Holi, people take this bhang and all. They drink a small amount of bhang. Their behavior changes. So very often, this all those psychedelic drugs are where people who do that. They are known as doping. So there, a small amount can change your behavior drastically. So that is the thing. So when we talk of doping, there are two types of doping in the semiconductors. One is substitutional, and others is the interstitial. So actually, uh, it is substitutional. Like in you very often in sports, you talk of substitute. Somebody is replacing the other. So that is the meaning of substitutional. So the host atom is replaced by the impurity. Then we talk of a substitutional impurity. And then the other case, see in crystal, this comes from the crystalline crystallography. There are sites that are empty where lattices are there. Then there are empty space between the lattice. That is known as interstitial sites. So if an impurity goes and sit in the interstitial site, then there is a different phenomena. Whereas in the substitutional sites, it give rise to a different kinds of properties. So that is, so there are two kinds of doping is possible. It could be substitutional or it could be interstitial. Yeah. So I think so again I think it's my time is running out, so we may discuss it like about this extrinsic semiconductor. These details we'll discuss. Already you are aware of it, but we'll have some discussion on this. Now, there's two questions. Before you come for the next class, I want you to think or about this. The question is, there are different kinds of we will be discussing it again, but still you know about n-type impurities, you know about p-type impurities. So how will you go about how will I select one particular type of impurity from different types of n-type impurities? Similarly, p. And then we will see that again the energy required for releasing free carriers from dopants are quite small. So why this happens? So I want you to think over it when we meet the next session. And I will be, of course, discussing these 2-3 slides which we have left. Well, it's okay, you are aware of it, so it doesn't need much detailed discussion, but still we'll be discussing. We'll start with that in the next. So if any questions, we can look into some questions if you have. Only one door. Yeah. Questions?
No, sir. No question.
Nithi?
No, sir.
Bhaskar?
No question, sir.
Neha?
No, sir.
Okay. So, okay, then we will continue our discussion with extrinsic semiconductors and the different properties. Then we will try to quantify, first qualitative discussion, then quantification, because that was one focus we'll be doing. And then we will wind up our discussion on this extrinsic semiconductors. Yeah, right. Okay.
Okay, sir.
Stop.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Okay.